Here we are. Look at the unit that we have been working on. We have already went through implicit related rates. We've used the first and second derivative to determine intervals of increasing and decreasing. You've had homework 36 assigned to you. We already worked on understand the graphical and numerical connections between F prime, and F double prime. And so that was where we were matching cards. Now we are in our last lesson. It's still the same title, Understand Graphical and Numerical Connections between graphs of F prime, and F double prime. After this, you'll have some homework. That'll be day 38. There's free response coming up. And then there's a quiz on the whole unit. Then there'll be a test on the whole unit. That includes everything you see on this page. Let's move on to last lesson. We are going to start with this. These notes are on the podium. You don't have these yet, so grab them if you have not done so. Okay, let's finish this last lesson. Graph below is the function of, got to pay attention to always what they're saying it is. It is F. It's a function. It's not a derivative. It's not the second derivative. I'm looking at the picture. It's just graphical. We're looking at it. Obviously, he's identified some relative maximum. He's showed us some zeros. Could be important. You never know. But these are always important things. State all the conclusions you can state about pay attention to what he wants, the graphs of the first derivative and the second derivative, and justify. So looking at this picture, what can we say about F prime? Well, obviously, since these two at x equals to -4 and 1, I'm going to write that out. X equals to -4 and x equals to a -1. F prime must equal to 0. Why? Tangent lines are 0. What else can I say about the first derivative? Notice what's happening from here to here till I get to that first extrema. Notice what I'm doing from this 0, and you know, I also lied. There's another. I should pay attention to this extrema. There's a third. Let me write that out. And x equals 2. That would be a -2. That derivative was 0. That's all I know about the derivative. There. Okay, back to where I was going here. From -infinity all the way to this first extrema is the same property as going from this second extrema to the last extrema. What's happening there? The slopes are all positive. So what can I say about f prime of x? F prime of x must be greater than 0 from -infinity to a -4. And then I'm going to pick back up at -2 and go all the way to 1. So -4 to -4 union, pick back up at -2 and go all the way to 1. Pick back up at -2 and go all the way to 1. what can I say about that interval and that interval? I can say f prime of x must be less than 0 from, that would be a -4, all the way to a -2, -4 to -2, union, where'd my other decreasing? -1 to infinity. What else can I say about the first derivative? Just a reminder, but that's all I can tell. I don't have any other information at the first derivative other than where are the extremas and where it's bigger than 0, where it's smaller than 0. Next column. What can I say about the second derivative? Just looking at the function. Remember what second derivatives are all about? They're all about points of inflection. They're all about concavities. So what can I see? Definitely, I see an area of concave down here. I also see another area of concave down here. That's concave down too. Matter of fact, they're side by side. But somewhere in there, there is some concave up here. So somewhere there's a change from concave up to concave. It can't be concave up and concave down at the same time. So I know that there's probably a point of inflection somewhere in there. But to keep it simple, let's see. I don't have, let's see, second derivative. It's really, really tough to stop the concave down. I don't know where to draw the possible points of inflection. F double prime of x has points of inflection. Points of inflection. He didn't give me anything, so I'm going to just use liberty to go in the middle. Put a dot here. They are evenly numbered, so he's probably doing us a favor. -2, let's see. 1, 2, 3, 4, 1, 2. I'm going to go up to here then. I'm going to put those two. I'm going to make an executive order and say that's a good. I'm going to call those my points of inflection. I don't really have proof, but I'm going to speculate it. What did I do on the left column? I answered good stuff, but I didn't justify. F prime of x is greater than 0 from this interval because... I didn't even do this with the extremas. I didn't even label which ones they were. They're equal to 0. No, I did say because... I need to say these are the derivative is 0. No, that's true. These are all true. I didn't say anything. I could start talking about what kind of extremas they were. Let's see. At -4 and 1, let me add that in here. At x equals to a -4 and 1, those were relative maxes because f prime of x changed from positive to negative. The extrema that I almost missed was at -2. X equals a -2 is a relative min because f prime of x changed from, I can use another word, decreasing to increasing. Those are my extremas. I said f prime of x was less than 0 from here because, I can say because f of x is, these were less than 0, so it was decreasing. The derivative was greater than 0. These were because f of x is increasing. It goes both ways. I can say it's increasing, and I can describe the derivative. I can describe the derivative and say it's because of the function. So there's still probably even more stuff I could say. All right, back to the culprit. I'm going to say f prime of x has points of inflection at x equals 2. My executive rule was -3. And I'm going to go with, this one right in the middle. So what I'm thinking here is this. I'm looking at concavity down. Let me put it in a darker color. Cavity down to here. Then it makes this great miraculous change to concave up here, and then miraculously it's concave down again. So now it's concave down again. So I see what's going on. You're not going to have concavity on both places at the same time. So somehow you're going to have to differentiate where it's changing. But anyway, back to, so f double prime has points of inflection at x equals 2 and -3, and I'm going to go with x equals 2. Looks like I put it at a 0. Let's see, what in the middle? In the middle. 1, 2, 3. You know, I'm going to change that. I can do that. I'm going to change it to, I'm going to put it at 1 instead. It looks better. Probably some of you were already saying that anyway. I mean, it's just guessing anyway. I didn't do any tests. I'm just guessing. So I'm going to go with -3 and 1. But before that, I probably should have said concavity. F double prime of x is less than 0 from -infinity to, and I'm calling it -3. Union, I got another concave down from, I'm calling it -1 to, it would be infinity. Because f of x, not f prime, f of x is concave down. F double prime of x is greater than 0, which means positive, between -3 and -1, because f of x is concave up. Therefore, what I'm doing, between these places, I'm putting those points of inflection at the -3, and I put it at the 1. And -1. -3 and -1 became the points of inflection. So that's what I put here. What else can I say about the second derivative? The second derivative, I already said it's increasing. That means greater than 0. So when I say greater than 0, that also could have been written as increasing. That could have also been written as the decreasing one. F double is greater than 0, F double prime less than 0, that would be decreasing. You'll probably think of things. If you think of something else that you can generalize from a picture, please send me a message. I'll add it to the slide. Think about that. If this was F and it was a cubic, that's interesting that F double prime would have had to have been the derivative. That would also have been a quadratic. Interesting. Because you take one power away. You can go the other way. If this was F, well, this was F, I'm sorry, F double prime is a quadratic. This is a quartic, 4th degree. So going backwards, if your function was, your first derivative would take 1 away, it'd be a cubic, then it becomes a quadratic. So those are possible. Next page. Given below is the graph of F prime. Okay, this is not F, this is F. State all the conclusions that you can make about the graphs of F and F double prime. All right, this ought to be fun. Okay, this is the derivative. What stands out? Let's see, the derivative changes signs here. The derivative changes signs here. The derivative changes signs here. And what does that mean about F when the derivative changes signs? When the derivative used to be less than 0 versus greater than 0 on the regular function, that meant it was decreasing to increasing. So this spot right here would be a relative min. And it's still a positive derivative here. It's still positive, but then it changed again. It went from being greater than 0 to less than 0. Went from increasing to decreasing. So I have a max here. It stays that way till it increases from less than 0 to greater than 0 here. So look at that. I have 2 mins and 1 max on the regular function. So that's what I'm going to do. I'm going to say f of x has relative mins at x equals to a negative 2, a 1, no, I'm sorry, negative 2, not a 1, that's a 3. Because f prime of x has zeros and changes signs from negative to positive. I can say f of x has relative max at x equals to, that was 1, because it is a 0, on f prime of x, and, that just means it's an extrema, but I can say because it's a max because because f prime of x changed from greater than 0 to less than 0. That means from above the axis to below the axis, whereas the minimums went from above the axis to below the axis. Let's see, did I do that right? This one went from, it was greater than 0 to less than 0. Yes, positive to negative, where the other one went from negative to positive. What can I say about f also? How about it where it's increasing and decreasing? The function, not the derivative, was decreasing here because it's below the axis, and it's decreasing here because it's below the axis. And it was increasing here because it's above the axis, increasing here because it's above the axis. So let me write that all out. F of x is decreasing from, that looks to me like a negative infinity to x equals to a negative 2, union, picks back up at 1 and continues to 3, because f prime of x was less than 0. I can add f of x is increasing from negative 2 to negative 2 to 1, and then picks back up at 3. Negative 2 to 1, union, picks back up at 3 and goes to infinity because f prime of x is now greater than 0. So I did my increase, so that's a lot. I'm going to leave that. Okay, now I have to answer the question is, what does this graph say about the second derivative? Not a whole lot. Because it's the derivative of the derivative. This is the derivative of the derivative. So it's no different than saying, let's pretend that this is f prime. What does it say about, this is f double prime. What does it say about f prime? What does it say? You can go backwards. I hope I'm not going to. Derivative of the derivative. Let's see. Well, this is a derivative. The derivative here is 0 here, just like we did on the other page. 0 here, 0 here. Because f prime changed from increasing to decreasing. So that made this a relative max of the, that would make that a 0 on the second derivative. And decreasing to increasing, this would be a 0 on the second derivative. So why don't I say that? F double prime of x equals to 0 at x equals to negative 1 and x equals to 2, because f prime of x changed signs. There. Now I can be more specific. I can say if they change signs. So those are zeros on the second derivative graph. What else can I say? Oh, if those were zeros, the second derivative went from negative to positive. Wouldn't that be, that would be telling me that, let's see what happened there. Concavity changed? Yeah. Let me talk about concavity. No, well, now concavity is with the first derivative. All I'm talking about is relative max. I mean, x equals 0. Those are intercepts. I was thinking that if this is the derivative, it looks like a cubic. Definitely looks like a cubic. That it's, if you take the derivative of a cubic, it becomes quadratic. I can also say, I guess I could say those things. I could say that on the other page too. I could have talked about that. I didn't even mention you can also say. Back to this one. Let's talk about where f prime of x is less than 0. That would be the derivative is less than 0 all the way till I get to this, and then all the way from this one here, just like we did the other problem, because f prime is increasing. Oh, I'm sorry. So that would be, I'm wrong. It would be greater than 0 then, right? Silly me. Greater than 0. F prime of x, with the ones I colored, is greater than 0. F prime of, we're looking at double prime, I'm sorry. F double prime of x is greater than 0 because, I didn't even get the interval. Interval on negative infinity to that mountaintop, -1. Yep, -1, union, and then it picks back up at the valley, which is a 2, and it goes all the way to infinity because f prime of x is greater than 0. And then between those two numbers, f double prime must be less than 0 because the slope of the derivative is negative. F double prime of x is less than 0 on the interval -1 to 2 because f prime of x is less than 0. Okay, that's a lot. This one more problem here. Below is a graph of f double prime. I knew it was coming. That's f double prime. State all the conclusions you can state about f and f prime. Justify your conclusions. Okay, study it for a second. Let's see what's going on there. What do I see? This is the second derivative, so I got to remind myself it's second derivative. And what do I know when the second derivative is 0? Those are possible points of inflection of the original function. I'm looking at it, that this second derivative was negative down here, and it's positive up here. So that told me there was a change of concavity on the regular function. Then it's still positive until it gets to here again. But the second derivative became 0, but it's still positive. It never crossed. So this is a point of inflection. This was a popoi. possible point of inflection on the regular function. I also have to realize this is a cubic. The original function had to be called a, let's see, 3, 4, 5, quintic. Fifth degree. That would have been f. F prime would have been a, if you take one away from quintic, that would be a quartic. Fourth degree. And then now we have the second degree, which is a cubic. So take one power away each time. So you can see there's a lot of stuff. That means, you know, it went from a higher degree to lower degree to get to the second derivative. Let me address what I just said about f. So that's negative. I can say f of x is concave down from negative infinity all the way to x equals to 0 because f double prime of x less than 0. I can say f of x is concave up from 0 to the 3. Union pick back up at 3 to infinity because it doesn't change, but it doesn't go past it, and it's 0 there. It's not greater than 0, nor is it less than 0 right here. So I can say it's concave up because f double prime of x is greater than 0, meaning there's a point of inflection on f of x at x equals to the 0 because f double prime of x changed from concave down, which means negative, to concave down to concave up, which means it's positive. So I've answered a lot about that function. I answered about its concavity. I answered about its points of inflection, and that's really what we use the second derivative for. Now let's talk about the first derivative. The second derivative is the derivative of the first derivative. So again, you can look at it as a f prime relationship. Forget that this is the second derivative. It's a derivative of something. The something happens to be the first derivative. I can tell a lot about the first derivative. I know that f prime of x must have been increasing wherever this graph is above the axis. So I can say increasing from 0 to 3 union 3 to infinity, because in terms of f double prime is greater than 0. I can tell you f prime of x must have been decreasing from negative infinity until it got to 0, because f double prime, its derivative, was underneath the x-axis, which means less than 0. Since there is a 0 at 0 and at 3, those are extremas. But at x equals to 0, let's see, f prime of x has a relative. Let's see, it went from negative to positive, negative to, has a relative min at x equals to 0 since f double prime changed from less than 0 to greater than 0. So I've described a extrema of the function. I've described the extrema of the derivative. I've described concavity. I've described a point of inflection. I described increasing and decreasing for both the first derivative and the function. Well, no, I didn't describe for the function. I described concavity. I think I've done enough damage. Calculator questions. Now, obviously, if I pull up a calculator, you're not going to see it. There's only this page. You have the last homework to work on to prepare for your quiz. The function of f prime of x is cosine of natural log of x. He says it's the first derivative of a function that you can take a derivative twice. So it's twice differentiable. The only thing that is not twice differentiable is a line. There's my interval 0 to 10. Find all the x values where f of x is a relative. It's interesting, where the function itself has a relative max or min. So you, obviously, this is a calculator. So you're going to graph it. So I'm going to graph it. I'll paste it. Cosine of ln of x from 0 to 10. I'll be right back. It'll just seem like a blink of an eye for you. Okay, I graphed it. Now I'm going to paste it. So it's probably going to pause a second here. Maybe not. Whoop. Too big. Make it small. There it is. And so on the interval from 0 to 10, find where there's a relative max or min. So where do relative max or mins occur? When your derivative is set equal to 0. So I'm looking, and beautiful graph. Just by looking, I see something happening here. You can double check on your graph. You can actually look for a 0. I didn't do any fancy calculation to see if that is. But it looks to me like there's a 0 there. And there's another one over here. There's another one here. So you have to find those. It's your job to find them. I'm going to double check with my calculator. Verify that's exactly a 5. And I'm going to have my calculator find my 0 over here. So that is your job. Oh, he said maximum. He said maximum. They're both not maximum. Maximum occurs when the derivative changes from less than 0 to greater than 0. This is greater than 0 to less. Let's see, I want a max. I'm sorry, it has a relative max. Greater than 0, that is the one I want. That is the one I want. I don't want this one. So I bet you it's 5. I mean, it looks so perfect. You verify it, please. On the same interval, find where there's a relative, minimum. That meant the derivative was less than 0 to the derivative, the slope is positive. So that's this one over here. If I was betting, I would say it's around 0.25. You find it. Use your calculator. You find it. On the interval from 0 to 10, find where there's a point of inflection. Point of inflection? Well, that's not the second derivative. That's the first derivative. I need to know where the second derivative is 0 and change signs. So that would be the derivative of the derivative. So I'm looking at my picture. All I can tell you is that the derivative of this derivative here is positive. Now it's negative. If the derivative of the derivative was positive, that's concave up of the original function. He is asking for the original function. Where would the f have a point of inflection? And let's see, it never changed. It stays negative forever and ever. So that's a whole lot of concave down. That's a little bit of concave up. Concave up. Whole lot of concave down. I'll bet you any money. Wherever that happened, wherever that changed, is a point of inflection. Your job, and they would say to James Bond, your job, if you are to take this mission, is to find it. Find that spot where the derivative, in other words, where is there a maximum of this function? Go to your calculator, graph it, ask to find the maximum. And go to the left and go to the right and find it. Because it was concave up to concave down, so it looked like that. It has to be it. It's your job. Find it. You can do it. And last problem. On the interval, how many relative minimums did G have? Oh, not F, G. G is this little bugger. That's G prime. I need, wherever G prime of X was equal to 0 would be relative max and mins of G. He's asking me to do the quotient rule. Well, let's do it. Let's, no, I'm not doing quotient rule. Gotta solve it. Sorry, of course, I'm not doing a second derivative. I want to solve it. That means the max or mins can occur at any critical number. The denominator could be 0, or the numerator could be 0. When this happens, those would be horizontal tangents at those extrema. When this happens, the derivative does not exist. Therefore, that would be a critical number where the derivative is undefined, but it could still happen at a cusp. It could still happen at a cusp. It could still be a max or min. Let's see. I don't even need a calculator for this. He's asking how many relative minimums does G have? Relative min, well, let's find out what these are. Where is sine of x equal to 0? Here and here. X can be 0. X could be pi. Where could it happen on here? X could be a -3, -2. That means there could be 3 relative minimums, but it's doubtful. Make a sign chart. -2, 0, pi. the derivative was 0. No, undefined. 0, 0. Plug in a number less than -2. I'm gonna plug in negative pi. Between -2 and 0, -1. Between 0 and pi, about pi over 2. Why am I picking these values? Because I'm looking at the first derivative and I have sine. And I know how to find the sine of pi and negative pi. I know how to find the sine of pi over 2. So I'm trying to keep it simple. Here goes, negative pi. What's the sine of a negative pi? Well, it's the same as going this way on pi. It's still, ooh. Never thought of a negative pi being in it, but we never use x's that are, probably we go from 0 to 2 pi when we talk about trig. And actually this graph, I'm sorry, we're going from 0 to 10. So I'm not even going to worry about this -2. What am I even concerned about? He said on the graph from 0 to 10, why didn't you stop me? I don't even care about this. So I don't even care about any of this. My job, what I'm wasting all my time. 0 to 10. Well, I do need to go past pi. So I'm going to go to 10. 2 pi is definitely bigger than pi. Okay, so here goes. What is the sine of pi over 2? That is a 1. And then 1 divided by a pi over 2 plus 2. A 1 over pi over 2 plus 2 is positive. So it's increasing. Try a 2 pi. Sine of 2 pi all the way around is 0. 0 over anything positive, still 0. Wait, 2 pi, he said go all the way to 10. I think it increases. Be quiet, mama. I think the problem has an error in it because if we're going all the way to 10, going to pi is a 3.14. Going to 2 pi is 6.28. Going to 3 pi, let's see, 3 times 3, that's still 9 something. So you're all going to 3 pi. And the problem is we only went, in trig, we only talk about going 1 repetition. The problem is if I go all the way to 3 pi, a lot of stuff happens because you have every multiple of pi will give you something. So if I go all the way, I only solved it to pi, but that would also mean where else is it 0? It would be 0 at pi, it's 0 at 2 pi, it's 0 at 3 pi. So I would have to actually go further and say I have 0, I have pi, I have 2 pi, and I have 3 pi. 3 pi. Every multiple of pi would give me a 0. So I actually would have to check between each of these, but it's always going to be the same thing. 0 to pi. And if I check between pi and 2 pi, anywhere, I could find the same thing. Well, actually, it's probably going to go to negative now. That's going to go to negative because sine's negative down here. And then 2 pi to 3 pi would be, again, positive again. So I think it's a bad problem, but he is asking for how many, if it was minimum means it would have to have gone from negative to positive slopes. So that's positive to negative. That's going to be this. This is negative to positive. So the most I can go, well, actually, before I get to 10, it'll be negative again. So, but negative to positive that does give me a minimum. So technically, I think I would have to go with 2. Oh, why am I working so hard? This was calculator allowed. Why don't we graph it and see if I'm right or wrong? And I'm okay if I'm wrong, because doesn't. It's a weird problem. So I'm going to come back with a graph, sine of x over x plus 2 from 0 to 10. Be right back. I'm back. There is the graph of the derivative from 0 to 10. Sure enough, I wanted to go to have a minimum. The slope has to be minimum max. He wants minimums. We want less than 0 to greater than 0. This is greater than 0 to less. It's not. This is less to greater. There's 1. And that would have been a minimum. Positive to negative. That's not going to cut it either. Did I have one over here? Let's see. No, that's 0. So it's increasing, decreasing. That would be a max. Decreasing. That would be a min. Decreasing to increasing. Does it happen over here? Positive to negative. Increasing to decreasing. So how many do I have? Let's see. I wanted from decreasing to going up to top. There's only the one. So I guess I'm wrong. I'll take it as calculator. I'll take that answer instead. Anyway, have fun. You have a quiz. I'll send you some extra problems, possibly. I don't know how much you have left in your papers. Adios. Before I go, get your homework done. You have a lot of work. I can send some miscellaneous answers, maybe later on today. And then it looks like that's it.